Alright, these are our notes for section 2.1 and 2.2 on inductive reasoning and logic. Most of this is going to be vocabulary. We do have one big example there in the middle that we'll look at, but again, most of this is vocabulary, so make sure you're following along and copying these down on your note sheet. Alright, our first definition is inductive reasoning, and inductive reasoning is reasoning that uses specific examples to reach a generalization. Okay, so I look at one little example, I look at another little example, I look at a third little example, I see what all of them have in common, and then I come to a generalization for everything, for all of the examples I looked at. Now, an example of this is finding a pattern. Alright, and I'm going to give you a pattern here. It is -5, 10, -20, 40, and we're going to come up with the next two terms. Now, the reason this is an example of inductive reasoning is because we look at these first two terms and we figure out, well, how can we get from -5 to 10? Well, we could add 15, and that's one way. Or we could multiply by -2. And I think those are really the only two ways. And now we're going to see which one of those holds true for our next specific example, which would be 10 to -20. Well, how do we get from 10 to -20? Well, if we add 15 to 10, we don't get -20, we get +25. But if we take 10 and we multiply it by -2, then we get -20. So now let's look at our third little example. We're going to see if this times -2 holds true for the third example. -20 times -2, well, that does give me +40. So now I know that this is my my rule. This is my generalization. We multiply by -2, and we found that by looking at three little examples: the first two terms, second and third terms, and then the third and fourth. Now I want you to come up with the fourth and the fifth. So we're going to take 40 multiplied by -2, and we get -80. Multiply by -2, we get +160. And that's an example of inductive reasoning. Now our next vocabulary word is a conjecture. And a conjecture is an educated guess based on known information. Okay? Now if you think about science, that's kind of the definition for a hypothesis in the scientific process. An educated guess based on known information. We look at the information they give us, and we come up with an idea or a generalization based on that information. Now a conjecture, so that was a conjecture. A counterexample proves or shows a conjecture is false. Okay, so if I come up with a conjecture for something, if I can show in any way or any example that it's false, that's my counterexample. And now this is what this example here is. It says, determine whether the conjecture is true or false. Give a counterexample for a false conjecture. So if it's true, you don't need to give me a counterexample, only when it's false. It tells us, this is our given information, that angle 1 and angle 2 are adjacent angles. And the conjecture they came up with, they're the educated guess on that known information, that given information, is that angle 1 and angle 2 are a linear pair. Now you want to figure out if that's true or not. So you want to ask yourself, is that always true, that conjecture, or sometimes true? Okay, if it's always true, if that always will work, that conjecture, then the whole thing is true. But if it is sometimes true, then it's false, and you need to give me a counterexample for it. So let's think about this. It says angle 1 and angle 2 are adjacent angles. Now remember, adjacent means that they're next to each other and they share a common side. And the conjecture they came up with is that they form a linear pair. Well, in a linear pair, they are adjacent angles. They are next to each other. But this is sometimes true because they don't have to be a linear pair. I can have adjacent angles that aren't a linear pair. I could have adjacent angles that are complementary. Okay? Those aren't a linear pair. They add to 90. So since this is sometimes true, it's false. And then you're going to give me a counterexample. And you could write out complementary angles. Or you could show me a picture. Alright, so there's our big angle, and we're going to split it into two smaller ones. Now these two angles are adjacent. Let's put 1 and 2 in there. They're adjacent, but they're not a linear pair. Okay? And that shows that our conjecture is false. That's all the notes for 2.1. Now we're going to go on to 2.2. 2.2 is on logic. Our first definition for this section is a statement. And a statement is a sentence that can either be true or false. Now it has to be one or the other. Our statement either needs to be true or it needs to be false. Okay, an example of that would be, let's say, the ink in this pen cast is green. Alright, that's a statement that could be either true or false. While you're watching this video here, the ink is green, so this is a true statement. Okay? That's what a statement is. Now, we can give a statement a name, and usually we use the letter P. P and Q are the two most commonly used. So I could say statement P equals this over here, the ink is green, and then instead of writing out the ink is green every time, I could just write the letter P. Now, to negate a statement means to add not, so that it's grammatically correct. You don't want to write out the sentence and then just tag not at the end. You want to put not in the statement so that it makes sense grammatically. So we're going to use our example there. The ink is green. We're going to negate it. And we would say the ink is not green. Okay? Now we've negated it. We added not to the sentence. Now this is a false statement at this point because the ink is green. So notice when you negate something, it changes the meaning of the statement. Our original statement was true. Now that we've negated it, it's false. And if we want to show negation, we use this squiggly line here, and this is called a tilde. Alright? That means to negate it. So what we just did is we negated P. Okay, we changed its meaning. The last thing we're going to look at is a compound statement. And compound statements are two statements joined by the words and or, one or the other. Alright, now we've got two different definitions for those. If it's joined by and, it's called a conjunction. And if we want to show that, we got to have two statements. We have P and Q, and we put like a caret pointing up. That's how we show it with symbols. P, upwards arrow, Q. Stands for P and Q. P is our first statement, Q is our second one. And this is what we could, I'll give you an example of one. Let's say the ink is green and these notes are for Algebra 2. Alright? There's two statements there. First one, the ink is green. Second one, these notes are for Algebra 2, and they're joined by and. That makes it a conjunction. Now, in order for this whole statement here, this whole compound conjunction statement to be true, both of these smaller statements, both P and Q, must be true. So we got to look at each one separate. The ink is green. That's a true statement. These notes are for Algebra 2. That's false. Okay, so the whole thing here is a false statement. I could change it. I could say the ink is green and these notes are for geometry, and then both of these statements are true, then the whole thing would be true. Since one of them is false, though, the whole thing is false. Last definition is a compound statement with or. It's called a disjunction. If we want to show that with symbols, P, and we have a downward arrow in Q. All right, P or Q. Again, two statements joined with or. The downward arrow is for or. So let's make this an or problem. Let's say the ink is green, or these notes are for, misspelled are for algebra 2. Now the first one's true again. Second one's false, just like before. But for this one, for a disjunction, only one needs to be true. Alright, and since this first one's true, the ink is green, then the whole thing is true. The ink is green, or these notes are for algebra 2. So only one of them needs to be true. If both of them are false, then it's false. Okay? But if one of them's true, then the whole thing is true. It's different than a conjunction, because for a conjunction, both need to be true. For a disjunction, for or, only one needs to be true. And those are your notes for section 2.1 and 2.2.